Okay, so I guess we will go with my atomic clock, and we will start now. And anyhow, this will be an introduction first. So perhaps there will be some more participants coming. So, well, first of all, it's a great pleasure to introduce Elchanan Mossel for, I guess, a number of reasons. But let me start with the personal. Elchanan spent some time at Microsoft, at that theory group at Microsoft. And that's in Seattle, and I'm also based in Seattle at the university. So although we never had joint collaboration or a paper, we, had a chance to chat and meet and so on. So it's a great personal pleasure. Now, a little bit more to the point on the scientific side. Elchanan is incredibly accomplished, and I know that some people don't like, citation numbers and so on. But I have to tell you that he published or co-authored about 180 papers. According to MathSciNet, he has 1,700 citations by 1,500 people. So, this could give you a sense of what he's doing. And, from my perspective, which is slightly different, Elchanan works on probability that is to a large extent discrete, and it's to a large extent inspired by computer science, by biology, even physics. And of course, among those, a huge number of papers, you will find lots of different topics, but these are like the main directions. And I would like to mention also specifically a result that made a lot of impact. It was very significant. So there was a paper on so-called noise sensitivity of functions, and those results somehow led to the solution of basically three major conjectures. They were called majority is stablest. The second one was called it ain't over till it's over, and the second one was related to max cut algorithm. I really cannot say very much more right now, but I have a feeling from a certain preview that I had that Elchanan will give a talk on a topic that is related to what I mentioned. And I guess without further ado, Elchanan, thank you for agreeing to give the talk, and congratulations on the medallion, because Elchanan, this talk is not just any talk, it's the medallion talk. So Elchanan will actually get a real medallion from the IMS, from the Institute of Mathematical Statistics. Please go ahead.
Thank you very much, Chris. Thank you very much for the very kind introduction. It's very nice to be introduced by somebody I've known and looked up to for so many years, and it was also a good opportunity to catch up. So of course it's a great honor to have been invited to give this medallion talk, and I'm really honored by the selection by the IMS. And I want to thank everybody who's come to this talk. I know that there are different people at different time zones, and also some of us are very tired of Zoom, so I appreciate everybody who's coming. And even though this is a medallion talk, I want everybody to feel very comfortable to interrupt me and ask questions on the chat. I'm not sure I see the chat, but I'll ask maybe Chris to monitor if there's a question on the chat. I'd be happy to answer. I think there's probably too much material in these lectures, but I mean, there isn't one single endpoint, so hopefully it will be interesting even if we don't go all the way to the end. Okay, so let's jump into it. I'm going to talk actually about something a little different than what Chris was referring to. I'm going to talk about something that I'm also working on for a very long time, essentially from the time that Chris and I know each other, which is quite a number of years. I'm going to talk about belief propagation, and I'm going to tell you about various aspects of this problem. Some of them are older, and some of them are newer, and some maybe better understanding that we have for these questions and for this model in current days. And I should mention that I was aiming to talk about an inference problem because this is the IMS. I was trying to talk about something that is both probability and statistics. So that was one of the reasons for this choice. So let's get started. Okay, so I'm going to start talking about this. The basic generative model or probabilistic model is this very famous model that's often referred to as the broadcast model on the trees or information flow on trees. And the process is very simple. This is a tree, and it's drawn from the top down. So sort of this is the root here. And I'm going to broadcast on this tree. This is some fixed tree, even though we are going to look at random trees later. And that's what we're going to do. We're going to choose a random color at the root. For simplicity, most of what I'm going to talk about is just going to be uniform distribution on a finite set of colors. So maybe I chose red, maybe there are just two colors, red and blue. And then what's going to happen at each round, I'm going to do the following. I'm going to copy the color of the parent with probability theta. So I'm going to toss a coin with bias theta. And if it says copy, I copy. And otherwise, if I don't copy, what I do is I choose a color uniformly at random, right? So there's not a lot of simplifying assumptions here, but somehow, the simplest model to analyze here is a model that I either copy or I forget everything that I know. And I chose a color uniformly at random. And this short notation here means uniform among the past set of colors, 1 to Q. So Q is going to be the number of colors. Okay, and I continue going down the tree. So here I went one level. Maybe here I decided to copy. Here I decided to copy. Here I decided to randomize, to choose a color at random, but this color tended up to be red, and so on and so forth. So I keep doing that, right? So, then I get some more red and some more blues, and some more red and some more blues. So that's the process that we're going to talk about. We're going to talk about large trees, infinite trees with many levels, or very large trees. And again, to simplify the presentation, I'm mostly going to talk about two types of trees. Mostly I'm going to talk about the array trees. So when I said the array trees, what do I mean? The array means that every node is D children. Maybe except the leaves. Maybe the leaves have no children, like in this picture, but everybody has D children. By the way, the picture that I have here is not a D array tree, right? Because some nodes have 2 children, some nodes have 4 children, and so on and so forth. And the other kind of trees I'm going to talk about is I'm going to talk about branching. I'm going to talk about branching process trees, right? So the kind of simple random trees that we like. Okay, so we have this process. We have a tree. It's either random or deterministic. It's very big. It goes for many levels. Start from a color at the root. We copy this color via this random processes. Now we're going to talk about an inference problem, and we're going to talk about the statistics and the probability of this inference problem. Okay, so let's just do a sanity check. Can we determine the root color from the color of the leaves? So obviously the answer to this question is no, this is impossible. It's impossible because there's randomness. Unless theta is 1, even if all the children of the root are red, it could be that the color of the root is blue. So we are in the realm of statistics and probability. This is not some deterministic algorithm problem, right? So there's a question in probability here. And the second question, which is brings us closer to statistics and probabilities, we want to estimate the color of the root. So can we estimate the color of the root? And what are we given? We're given the color of all the leaves, right? So we go with this process for certain number of generations. So this is from colors at the leaves. Okay, so we want to estimate from the color of the leaves. We want to estimate the color of the root. Okay, so again, there is still not a lot of interesting probability here. This is called Bayes rule, or the fancy word for Bayes rule is belief propagation. So there is a very simple recursive application of Bayes rule that allows you to compute the posterior at the root exactly given the leaves. So you can imagine, we know this for one color. If I tell you that this is the parent and this is the child, and I tell you this is blue, and I tell you this is red, you can apply Bayes rule and compute the posterior probability that the root is either blue or red. But it turns out that you can even do Bayes rule recursively. And when you do Bayes rule recursively, what you get is you get this algorithm that's called belief propagation that computes the posterior probability exactly at the root, and it runs in linear time in the size of the tree, so that's very nice. So, if you are doing applied machine learning, you're done, right? There's an algorithm that solves the problem and you don't care about it anymore. However, for us, we will talk about the statistical property of this estimator or the probabilistic properties of this estimator, and that's going to be the main topic of this talk. And I'll just mention that, usually when people talk about belief propagation, they are talking about non-tree graphs, graphs with cycles. I think Pearl is famous for using belief propagation in the 80s, but of course people use them in trees even before in statistical physics and in biology. So that happened way back. Okay, so that's the basic problem. We're going to talk about sort of large questions of this type, about the properties in terms of the inference and the statistical properties. Okay, so I'm going to talk about, there are going to be maybe 2 or 3 parts to the talk, depending on how well we're doing. And I'm going to start with the easy case. And the easy case actually started with a fundamental paper by Kestem and Stigum in the 1960s. And this is what I now call the linear theory. And somehow the linear theory I will talk about only in the case where Q, the number of the colors in the model that I talked about, Q is the number of colors again, is equal to 2. So it turns out that this model has features that make it very linear when Q is equal to 2, and makes it very nonlinear when Q is large. And I'm sure one question you'll ask me is for what values it becomes from linear to nonlinear, and I'm going maybe to talk about it later. First of all, I want to tell you the case that we understand the best, and that's the case that Q equal to 2, and that's the linear case, and the work of Kestem and Stigum will play an important role there, right? So Q is really just the number of colors, right? So the model is either 2 colors or 3 colors or 4 colors, and it's this copying or broadcast model that we talked about, and the number of colors is really going to play an important role. Okay, so let's talk a little bit about the probability here. So we are going to fix the number of colors to be 2. We are going to look, at H level. So the number of levels is going to be H, D arbitrary. And sort of the picture that you should have in mind is that the tree is becoming bigger and bigger, right? So there's going to be H levels, but H is going to infinity. And because we are doing mathematics and not just pictures, we are going to call the 2 colors we're going to call the 2 colors +1 and -1. Instead of red and blue, it's much better to call them +1 and -1, right? So that's a good setting for us to work with. And now let's try to think about the most basic random variables here. So the most interesting random variable, the random variable that we care about the most, is this x0, the color of the root node. And there's going to be a vector of colors, xh. So I'll draw the same picture again. So if this is level h, xh is a vector. It's the colors at level h. And there's a very natural thing that you might do as a statistician or a probabilist. You say, well, I don't like vectors. I'm going to work with the most natural random variables that you can look at. And this is the sum of all of the coordinates of this vector, right? Each leaf is either +1 or -1. You can sum all of these random variables, and you can ask, how do these random variables behave? If you think about it, this is not a priori clear for anybody who's just doing probability. These random variables are very far from being independent, right? These random variables are not independent. There's dependence between them. But, the first thing that we do in linear probability is we sum random variables and we ask, how do they behave? Okay, so there's a lot of information here, but let me tell you what Kestem and Stigum proved in 1966. Okay, so this is more than 50 years ago. They proved that something interesting is going on here. There's what we call these days a phase transition. They said there's really different behaviors depending on the product of 2 quantities. D, how fast the tree grows, and theta, what's the copying or what's the non-noise level. And there's 2 different behaviors if d theta square is less or equal than 1, or d theta square is bigger than 1. Okay, so so what are the 2 parameters that are competing here? the more I duplicate, the better signal I have, and the better probability I have copying versus randomizing, the better quality of signal I have. So these two quantities are going in the same direction. And if they're big, something happens, and if they're small, something else happens. So let's start with the case where they're small. That's the case that's closer to what we're used to in probability. So they show that if theta square is less or equal than 1, then if you look at S of h and you normalize it appropriately, so you normalize it, by what you should normalize it, then what you get is you get a normal law. You just get what we like in probability the best, which is a normal random variable. And moreover, this normal random variable is independent of the choice of x naught. So it doesn't matter if you started from a plus 1 at the root or a minus 1 at the root. The random variable that you get, the normalized random variable that you get at least, is going to be just have a normal law, and it will give you no information about it. On the other hand, if t theta square is bigger than 1, then S of h converges to a non-normal law, and this non-normal law is actually depending on x naught. So you get one distribution if you start from x naught equal to plus, and another distribution if you get x naught is equal to minus. And a lot of what I'm going to talk about is going to do with this threshold. So d theta square equal to 1 is referred to as the Kesten-Stigum threshold, and we're going to talk about it quite a bit. Okay, so that's the Kesten-Stigum threshold. This is the understanding, the basic statistical understanding of what we want to understand is what do we know about the lifts from the root in this process of broadcasting, right? So for those of you who might have joined late, right, we have this process of we copy with probability theta, we do set a tree where every node has d children, and we are trying to understand how much information is there in the lifts about the root. And the Kesten and Stigum, the result from 1966, showed there's a phase transition. If you just look at the sum of this vector of all the colors here, d theta square is bigger than 1, then you get a random variable that depends on the root. If it's less or equal to 1, then it's independent of the root. Okay, sorry. So I didn't know this is not going to fit into the slide, but so this is 1966. Something that happens in the 90s is it turns out that this is the right threshold for this problem, and it's the right threshold in the following sense. So if d theta square is less or equal than 1, then it's not only the case that the sum of all the random variables is independent of the root. In fact, the vector of random variables is independent of the root, and I wrote it in this compact way here. If you run belief propagation, what would it tell you if the leaves are independent of the root? It will tell you that the root is equally likely to be plus or minus. Right? So this is the statistics way of saying that the root and the level h are independent. In other words, what the theorem from the 90s says is that belief propagation infers non-trivially if and only if. So belief propagation is this recursive application of Bayes rule if and only if a majority infers non-trivially. And so this is our results from the 90s. There are multiple proofs. I mean, starting for statistical physics by Blecher, who is in Zagrebnov, and then a bunch of other proofs. Okay, so let me maybe show you a picture. So this is how it looks like. I think sorry I didn't write the parameter. So this is a problem of everything that I'm doing is for q equal to 2, t equal to 2. So the tree is just the tree with every node has 2 children. And now I'm looking at this random variable sh, which is the sum of all the nodes at level h. And that's the random variable I look at. And if I remember correctly, I forgot for how many levels this goes, but maybe 10 levels or maybe 5 levels. But if I remember correctly, this is the case where theta is equal to 0.7. So d theta square is less than 1, and here is theta equals 0.9. And what you can see here, Kesten-Stigum theorem is telling us that this should behave like a normal random variable. And here Kesten-Stigum tells us this is not a normal random variable. And in fact, we know a lot about this random variable. So if you may suspect that this random variable is a mixture of 2 Gaussians, you are wrong. This is not a Gaussian random variable, even if I tell you that the root is plus. So the two modes of a random variable are not Gaussian, so this random variable is more interesting in this setup. Okay, and so maybe this is a good time. I really want question. I don't know what my chance of getting questions, but if there are questions, I'm happy to take one. I even see the question and answer, so this is a good time to take questions. Otherwise, I mean, I'm going to talk about one or two quick applications of that, because I tell you before I tell you a little bit about the nonlinear side of the story. And if some of you joined late because of other talks or something, and you want me to review something, that's a good time to do that too.
Well, you can submit questions by chat or by raising the hand.
Okay, good. So yeah, feel free to do so. So I know I always talk too quickly, but I'm actually not in a rush. So I just give a false impression. I'm definitely not in a rush. Okay, so I want to give two quick application. I mean, this sounds maybe like a very idealized process, this process of broadcasting on tree and trying to figure out the root from the tree. I just want to mention two quick application of this process, and maybe before maybe one, maybe two quick application of this process. Let's try to see how many of you are alive. Okay, can people raise their hands or not? Or just ask a question? Okay, maybe I won't do that to you. I wanted you to vote which application you want to see. So, but I won't do that. Okay, so let me just mention two quick applications. So one application is for phylogenetic inference. Maybe I'll go over this very briefly. So phylogenetic inference, the goal is a little different than what we were talking about right now. The goal is to do what Darwin did. Darwin was actually trying to build an unknown tree. So Darwin was trying to build this tree over here. And what did he want? What did he build this tree based on? He built this tree based on the morphology of the birds that he was looking at. What people do these days is they build these trees based on the DNA sequences that they have for different species, and they don't know what's the family tree that relates them. So this is a very active tree of mathematical biology with very nice contributions since the 50s or the 60s. And they have models that are very, very similar to the model that I talked about now, except you don't know the structure of the tree. So you don't know which vertices, which leaves are sisters, and which leaves are cousins, and which leaves are second cousins, and so on and so forth. And that's what phylogenetics try to do. So one point of view that I like of phylogenetic is this point of view, right? So you have exactly the broadcast process on the tree that we've seen before, but what happens is that, you know, we don't just apply it once, we apply it many times, right? So these pixels here are supposed to represent the DNA sequence of this species, and then, you know, there's a speciation, there's speciation, so there's speciation here, and there's speciation here, and speciation here. And whenever you go down the tree, there are arrows. The arrows are exactly what correspond to the broadcast process on the trees, and you get all these sequences over there. So in the original question that we talked about, the broadcast problem, what we wanted to do in the broadcast problem, we wanted to look at all of these DNA sequences here, and from these DNA sequences here, we wanted to reconstruct this guy. In the phylogenetic problem, the story is a little different because we are getting this sequence, and 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 this sequence, but we don't know that these two sequences come from sister species, right? We don't know that they're siblings. So we're giving them in some random order, and the goal is to exactly recover this tree. Okay, so it's a different problem. It's a problem that people, you know, there's a lot of software that biologists use to do this all the time, you know, indeed for prehistoric bacteria and other animals, up to like doing it for influenza or viruses that we're studying right now. Even for COVID, people use phylogenetic tools. So this is something that people in molecular biology do a lot. And let me just tell you what is the mass that comes from this Kestenstigon phase transition. So there was a sequence of work since the beginning of the 2000s that essentially says the following. So there is a mathematical model. I didn't really tell you what the mathematical model is, but for a phylogenetic tree T on n leaves, leaves is the number of species that you're working with, and a binary DNA, so not A, C, G, and T, but binary DNA, which people in biology often use. The phase transition that we've seen of d theta square equal to 1, so d in this case is always 2, has a very interesting manifestation in terms of how much information you need. So in particular, the sequence length that you need, right? So how do you reconstruct this phylogenetic tree? Yeah, well, you send some biologists to sample DNA sequences, and then from this DNA sequence, you try to recover the tree. So it turns out that the Kesten stigma phase transition plays a very important role here. So if 2 theta square is bigger than 1, the sequence of lengths that the length sequence that you need is logarithmic in the number of species, right? So if you have a billion of species, maybe you can do it with 20 or 30 with DNA sequences that are very short. If 2 theta square is less than 1, then the length of the sequence that you know is the power of the size of the tree, right? So if you have a million of species, you know, maybe you need an order of a million or square root of a million or million square, a billion square. It depends on the actual parameter data. We have upper and lower bounds. But this phase transition is very, very rapid at the point at the Kesten-Stigom bound. And that's one manifestation of the Kesten-Stigom bound that we see for this other inference problem, the inference problem of recovering a phylogenetic tree from sequences. So this is really a statistical problem that people care about. And of course, you can ask what happens in practice. Is 2 theta square bigger than 1 or less than 1? But that depends on the biological setup, right? If the species that you're looking for looking at are very far evolutionary, then theta is very, very close to 0. If the species that you're looking at are very, very close to one another, if they're mammals or something, then theta is actually very close to 1, and there are other effects that's come into play. Okay, so that was one story. Another story.
Okay,
I see a question. Yes, you want to? Somebody raised their hand. Do you want to ask a question in the chat? Or
let's see if we could give allowed to talk, but I have to find that person on the list. Okay, so it's either chat. See, because the hand is gone, so I cannot.
Okay, maybe it was a mistake. Oh, okay, somebody wrote something.
He has left this session. Okay, looks like he has left this session. Okay.
Good. Okay, so let me maybe mention one more application of this or one more instance where this Kesten-Stigom bound played a role. This may be something that more of you have seen. It's this block model, this random graph model. So I'll tell you what the model is. It's a random graph model on n nodes. And unlike the Erdős-Rényi random graph, the nodes have colors, so half are plus and half are minus, so half of blue or half are red. And then what happens is that two nodes of the same colors are connected with some probability. And for us, it would be useful that this probability is this number d times 1 minus theta over n plus 2d theta over n. And two the nodes with different colors are connected with a smaller probability. It's just the second term that we had before, this t times 1 minus theta over n. You can just call this number a over n and b over n. But for us, this theta would be exactly the same theta that we've seen before. And that's why I chose this parameterization. Okay, so we have a random graph, half are blue, half are red. Maybe in the US, Republicans and Democrats. Republicans like to talk to Republicans. Democrats like to talk to Republicans. They talk less to each other. And that's the only features of the model that we have. So it's a very simplistic model.
So let me interrupt. D is 2. What is D?
D can be any number now.
But what does it represent?
So yeah, okay. So very good. Thank you, Chris. So D is going to be the average degree. So the reason I chose this parameterization, thank you very much. So D is going to be the average degree, and theta is going to be the covariance of neighboring opinions. Okay, so this is a random graph, like the Erdős-Rényi random graph. The average degree is going to be D. There's also these opinions. The opinions are plus and minus, but they're correlated. Neighbors are more likely to have the same opinion, and in fact, the covariance between your opinion and my opinion, if we're connected, is going to be theta. If there's an edge between them. That's why I chose this parameter. Thank you. Okay, so yes, sorry, so it's even written on the slide. Sorry, the average, thank you for predicting it. The average degree is D. And if U and V are neighbors, then the expected value of XU and XV is equal to theta, and that's why we chose the parameters. And the obvious inference problem is we want to know which nodes are likely to be red or blue. Of course, there's a lot of symmetries here. You know, you can switch all the red and all the blue and all the blue and all the red and so on and so forth. So you have to take this symmetry out. But just so we make clear that the inference problem is clear. Okay, sorry, I'll just maybe one more piece of text and then I'll show you some picture. So what got me and my collaborators, especially Joe Neiman and Alan Sly, into this picture is this conjecture by the physics or the statistical physics community, the Sel, Kazakala, Amur, and Steberova, is that belief propagation is the optimal algorithm for solving this problem. And it's possible to do better than random classification of these two communities, if and only if d theta square is bigger than 1. So again, the
okay, Elchanan, I will interrupt you once again. You see, when you say inference, in your original model, you were trying to guess the color of the root, given the bottom of the tree, the leaves. So in this case, what is given and what are you trying to guess?
Very good. So I'll get to that in a second. There are a lot of mysteries here. So first of all, in the case that we're going to see in a second, you are going to be given no information about the colors of anything. The second thing is my graph is not a tree anymore. So what does it mean to apply belief propagation? The third thing, when I apply belief propagation, I have to start from some colors and what colors I'm going to apply them to. Okay, so I won't have time to address all of these questions. I'll just maybe address them quickly. The belief propagation, the physicists use the belief propagation where you assign people colors completely at random. You pretend that your graph is a tree and you run the iteration of the base rule of belief propagation. Okay, which is something very, very different than what we've seen, but somewhat related, right? The colors are random, but they have nothing to do with the actual colors. You run these algorithms that, you know, assumes that the colors are correct and does some stuff. And they predicted that the threshold is exactly the same threshold. They wrote it in terms of A and B, but they knew that it's the Kesten-Stigum bound because the Kesten-Stigum bound appears there in other questions, what's called replica symmetry breaking. So this was the fast answer for Chris. Let me show you sort of the more pictorial answer. So this is how maybe a sample of the model looks like. So, you know, we have a bunch of red and blue, but that's not what we see when we solve the inference problem. What we solve when we see the inference problem is this picture. It's exactly the same picture, but without the colors. Okay, so we are given this picture without any colors, and our goal is to recover this back. Well, maybe not this back exactly. If you think about it a little bit, you know, this is a sparse graph. Like I said before, even one node, even if you know all the neighbors, you cannot know, but you want to do better than random. You want to recover the partition to blue and red that has correlation more than 50-50 with the actual partition. Okay, so again, the data, there's just one sample in the data. The data is just this sample with no colors. And the goal is not to recover this because this we know is impossible for two reasons. First of all, there's symmetry between blue and red. So this picture and the flipped picture of blue and red is exactly the same to us. But more importantly, because this graph is very, very sparse, there are a lot of isolated nodes. You cannot say anything about them. Even nodes of degree 10 or 11, you cannot really say anything about them, even if you know all their neighbors, but you still want to do something better than 50-50. Okay, so that was the conjecture in physics that got many people, including my collaborators, Joe Neiman and Alan Sly, very excited about it. And I'll very briefly tell you where the Kesten-Stigum bound comes into this picture. I won't have time to tell you all the stories. So Chris asked excellent question. You know, this is not a tree. We don't have any colors. What does it mean to apply BP? Some of these questions we understand pretty well right now, and some of these questions we still don't completely understand. So I'll tell you what we know, and we know quite a bit. Okay, so first of all, the basic answer is that the conjecture by the physicists is correct. It's possible to infer the partition better than random, better than 50 and 50, if and only if you are above the Kesten-Stigum bound. So that's just true. I mean, what they conjecture, the basic conjecture that they made is true. Okay. Now, I'm not going to tell you why this is true. I'm just going to give you hints why this is true. So it's a long line of work. Maybe since Chris expressed interest, I'll tell you a little bit about the first result with Alan and Joe. Then, so this showed that it's impossible if d theta square is less or equal than 1. Then, sorry, I didn't mean to delete Mossel names, but then there was a paper by Mossel and a parallel paper by us that proved the positive direction. And then there was a sequence of better work, including by these guys, Bourdonnais, Lelarge, and Mossel, and some works by Abe and Sandon, and other works, beautiful works that, you know, get more and more of the picture of what's going on here. So it's a long sequence of work that I'll try to summarize or give a hint to very, very briefly. And I should say that a lot of the insight, especially for the positive direction, for the harder results, came actually from a joint work with the physicist. So we have this joint work with Kazakala, Moore, and with Neiman and Sly, and Zdebova and Chang, which says, you know, what you have to think about BP here is you actually have to think about it as an operator, and you have to linearize this operator. Okay, so that's a major insight from that work. So again, we see the Kestenstiegum bound. I have a feeling that if I tell you the story in too much detail, that's all I'm going to tell you. And I feel like talking a little bit about the nonlinear things, which we understand less. So I'm just going to, okay, I'll tell you a little bit of the stories. Chris asked, so you know, I'm sure other people are interested. So let me give you a cheaty sketch of the easiest result here. So the proof I'm going to tell you is not correct, but it has something to do with the actual proof, and it's, you know, the easiest and the first result that we proved it. And this is the easy direction. So if d theta square is less than 1, then it's impossible to infer better than random. The actual proof is much more complicated, but it is based on the intuition that I'm telling you right here. Okay, so this is the picture that we have, and I'm going to tell you why is it true that if d theta square is less than or equal than 1, we cannot infer that better than random. So what does it mean to infer better than random? We have to think about it. So if I can infer better than random, then if I'm given 2 random nodes, this node over here and this node over here, I should be able to say with probability better than 50% if they have the same color or a different color, right? Because we have the symmetry between the blue and the red. So it's not really about the color, it's about the equivalence classes. And you know, it's just looking at these 3 nodes, and I want to understand, you know, if they're the same color or not. And again, these are not neighbors. Neighbors, I know they're likely to be of the same color, but I look at 2 random nodes, and I want to know how likely they are to be the same color or not. And I want to say that this probability is going to be 50-50 if d theta square is less or equal than 1. That's my goal in the easy direction. Okay, so I'm just going to show you the proof in picture. So let's see what changes from picture to picture. So you have these 2 nodes here. They are both green here. They're arbitrary node. Green is the mixture of blue and red. So let's just fix one of them. So I'm going to say that you know that this node here is going to be red. And I want to know, is this going to affect the probability that this node is going to be red or not? Or is it going to stay half-half when I condition on this fact? Now what I'm going to do is accept, in addition to the fact that this node is red, I'm going to be very generous to you. And I'm also going to provide all the colors of all these nodes. So in this picture, these are all the nodes at distance 2, but you should really think about it as all the nodes at distance like log n over 100. You know, some nodes very, very far away, but you know, still within the gears of this random graph. Now, why does it help me? It helps me for 2 reasons. First of all, okay, here's one big cheat. By the Markov property, this is sort of a Markov random field. Once I tell you that I condition on these guys over here, on all the guys at distance log n over 100, you don't care about this guy anymore. They're conditionally independent. And the other reason, and that's the main reason, is what I have in this yellow picture over here. This is just the broadcast process on the tree that we started from at the beginning. We start from a node, we copy with probability theta, we go do it over and over again. It's not on a deterministic tree of the greedy, it's on a branching process tree, but the results carry for that. Okay, so somehow locally in this block model picture, what we have is the tree broadcast picture. And because we have the tree broadcast picture, in the tree broadcast picture, even if I'm given all these colors, which I'm not given, I cannot recover the color of this node. And this tells me that in this case, I cannot do better than that. Okay, so that's sort of the easy intuition, and making it into a proof requires some work. In particular, we also need to work that Evans, Kenyon, Peres, and Schulman, which proved the branching process version of the d theta square equal to 1 threshold from the early 2000s. Okay, so I'll just give you a hint for the hard direction. So this was all the easy direction. For the hard direction, the interesting object that comes from linearizing BP is this called this non-backtracking walk matrix. And in this non-backtracking walk matrix is a random matrix, but it's not symmetric, it's not normal. The spectrum is complex, and it's very interesting. You get pictures like that for the model when you simulate it from data, and you get pictures like this if you actually run it on real networks. And again, both of these pictures are from the work from the physicists, I think, which really, a lot of the intuition about why BP works in this case, where you actually have no colors at the beginning. And so it's really some, new kind of linear algebra that you have to think about that is motivated by this understanding of belief propagation. Okay, this is another good chance to take a break before I tell you a little bit about the nonlinear part of the story, which is where there are more mysteries and there's less we know. Okay, so let me continue with the nonlinear theory. So now I'm going to talk about the nonlinear theories and what it, in terms of our simple model, what it talk about, it just means that the number of colors instead of being 2 is going to be large. And I'm going to already, since I won't have time to talk about all the detail, large means bigger than 5, right? Up to 4. 4 is an interesting case, but 2 and 3 are small, and 5 and higher are large. And when Q is large, there's a different story that's happening. And I'm trying to tell you a little bit about this story. We'll see how much time we'll have. So first of all, everything that we knew how to do before, we still know how to do. So let me tell you an example of what do I mean by that. So claim for all Q, any number of colors, if you are in the good regime, if d theta square is bigger than 1, if Kesten and Stigm tell you you're in good shape, then you can do whatever you wanted to do before. So for the tree broadcast model, you can distinguish, or you can recover the root better than random. You can detect in the block model, you can find these 2 communities in the block models, and you can recover phylogenies or this evolutionary tree from order log n. It's exactly what we knew in the case of Q equal to. Nothing changes as long as d theta square is greater than 1. So I won't give you the general proof, I give you the cheating proof. So the cheating proof is just in the case when Q is even. So Q is some even number. And then the easy way to do it is just say, well, I have Q colors, maybe I have 10 colors. I'm going to call 5 of them plus and 5 of them minus arbitrarily. And I'm going to ignore all the other details of the model. And then you just see that all of the models that we talked about, the broadcast model, the phylogeny model, and the block model, all project to the Q equal to model with the same theta. So it's just a very simple reduction to the case of the 2 communities. When Q is odd, you have to do some work, but let me not talk about this work, right? So everything that we knew how to do before, in this, when d theta square is bigger than 1, we can still do, and we can still, in fact, we can do it by direct reduction for the case that Q is equal to 2, at least when Q is even. So let me skip what you do in the more general case. The more interesting phenomena is that you can sometimes do things even when d theta square is less than 1. Okay, so when d theta square is bigger than 1, it's exactly the same picture that we had before. But for large Q, and again, this is going to be Q bigger than 5, there exists a theta Q below the Kesten-Stigm bound. So d theta Q square is less than 1, and such that in this interval between the Kesten-Stigm bound and your theta Q, you, for the tree broadcast model, you can distinguish, or you can recover the root better than random. You can detect, you can find community better than randoms in the block models, and you can recover phylogeny from sequences of order log n. So all the 3 tasks that you can talk about, we talked about before, now you can do in an interval below the Kesten-Stigm bound. But I left some space here. Why did I leave some space here? Because there's always a twist. You can distinguish, you can find the root, but you cannot do it using linear estimator. You cannot just do it by summing the guys. Or you cannot do it using robust estimators. Your estimators have to be like BP. They have to know who is the brother and who is the sister of who, and who is the cousin of who. And if you apply a little bit of more noise at the leaves, your estimator is going to fail. So something much more fragile is going to happen here. You can detect in the block model, so you can find partition in the same way that you did before, but before we had an efficient algorithm to do it, and now this is conjectured to be one of the cases where you have a computational and statistical gap. So you can do it information theoretically. You can, in exponential time, go over all possible partitions and compute something like the likelihood and then find a partition that's correlated, but we have no algorithm that does that. Okay, and people believe that maybe there isn't an algorithm that does that. And similarly for phylogenies, we believe that this cannot be done robustly. So somehow everything that you could do before, you can now do for a bigger interval, but once you pass the Kasten-Stigum bound, everything becoming much more fragile. Everything is depending on where the things sit, and they're very, very sensitive to noise, and you know, maybe you can do it, but it requires exponential time, but maybe you can do it, but you need to know the parameter exactly, so things are much, much more fragile. So there's sort of a different picture, a more mysterious picture for large Q. So I thought of giving you the easiest proof of in this regime, and this is this regime. This is when you have the quantifiers. Like maybe I'll just talk about it for 2 minutes, and then I'll go to the last part. So the easiest regime is so remember the Kasten-Stigum bounded d theta squared, but that's not what we're doing right now. We're in a different regime, and the result says that as long as d theta is bigger than 1, if Q is large enough, if Q is bigger than some Q theta, then in the problem of recovering the root from the leaves, you can do better than random. And I'm going to cheat. Okay, so we just have the broadcast model on the tree. D theta is bigger than 1. You tell me maybe it's 1.1. I'm going to choose Q to be 200, and I'm going to show you that I can do it better than random. In fact, I'm just going to tell you the proof for Q equal infinity. Okay, so what is the proof for Q equal infinity? I have infinitely many colors, right? So I choose one of my infinitely many colors at random. I choose color number 7. And what happens in this model? I copy with probability theta. We have to think what is the model for Q equal infinity. But the right limit of the model is I copy with probability theta. And otherwise, when I'm not copying, I'm going to choose a number that I've never seen before and I'll never see again. Okay, so maybe here I copy, so this is going to be a 9 again. But here I copy, and this is going to be a 9. Here I don't copy, so it will be a completely different number. It will be 11, here it will be 25. So, and the order doesn't matter. So what happens in this model? When will I know, in the case Q equal infinity, when will I know something about the root? I will know something about the root if I see the number 11 here and the number 11 here. The only reason I can see an 11 on the left subtree of the root and the right subtree of the root is if the root is 11. Okay, so here you see the flavor of branching processes, right? I want this to hold for many, many levels. So I want the branching process of copying to be supercritical. And it will be supercritical exactly if d theta is bigger than 1. Now, you don't get all the picture from it, but what you get is you get something interesting. It's not about the number of 11s, it's about where the 11s are. So I could have, you know, the number 25 can appear 30 times here. That's irrelevant. The fact that I have an 11 here and 11 here means that, oh, the root is going to be 11. So that's for the case Q equal infinity. When Q is large, what you're looking for instead is just one witness here and one witness here. You're sort of looking for a large fractal. So you're looking for a large fractal of a certain color, and that's going to give you the estimate that you know that your root is your root. Okay, so I'll stop with that. I don't want to tell you more about it because there's a lot to say, but you know, including actually, you know, the formal proof confirming the conjecture by the physicists that the critical value is between 4 and 5 is work by Alan Sly again, who used some other methods which I won't have time to talk about. So I want to, maybe because I'm running out of time, maybe I'll just mention a little bit, you know, of the result about the complexity of BP. I'll really do it in 5 minutes. I won't really talk too much about it, but so what is BP? Remember, belief propagation is this algorithm we started with at the beginning. You have the leaves, you want to recover the root. There's this very simple recursive application of Bayes' rule that gives you the posterior of the root. And now I want to talk about the complexity of this algorithm. This talk started from the premise that this is a very simple algorithm. So it is simple. It runs in linear time. But now that we understood that, above the Kasten-Stigom bound, something interesting is happening, it's not a linear algorithm, we can ask, is it really simple? And the two questions that I'm going to ask, sorry, there's a typo here. So it uses real number. Should it really use real numbers? I mean, so it's updating probability. Can you just, the original process just use colors. Can I just use colors to go back? And it uses some depths, right? This is a recursive algorithm, it uses depths. And depths is something that we think a lot about, in particular in the context of deep nets. And the question is it really needed? Okay, so wait a second, is it really related to deep net? I think it might be related to deep nets. I'm not sure everybody agrees with my picture. So let me just try to convince you in one slide, why do I think it's related to deep nets? Or mathematically it's related to deep nets. So this is one of the ways I think about deep nets. So there's a lot of we don't understand about deep nets. And one way I like to think about deep nets or deep inference in general, the way I like to think about it is to ask the following mathematical, more abstract question. So mathematically, for me, it is natural to ask if there are good models of data that satisfy three, what I call natural criteria. So first of all, there is realism. We want a reasonable data model, right? So IID coin tosses are, for me, realistic. And, Gaussian distribution are realistic. Something that looks realistic, for me, the broadcast model on the tree is realistic. The other thing that we want from this model is we know how to build deep nets, so we should be able to reverse engineer the model. So reconstruction, there should be a provable, efficient algorithm to reverse engineer the generative process. So for me, this is done because, this is a realistic model. It's used in biology, it's used in vision, it's used in other places, this broadcast model on the tree. Reconstruction is there an algorithm that from samples can recover the graphical model, can recover the tree? And this we saw that we've seen that the answer is yes, this is this phylogenetic reconstruction. And the last aspect is that we want to prove that in some sense depth is needed. Okay, and this we haven't talked about. So we didn't talk about the fact that this process actually has these layers, and for some things that we do, maybe for recovering the root from the leaf, we actually need these steps. So I'm running out of time, so I'll just give you a hint about this result. So these results come from the language of circuit complexity, so it's not something that I'll throw out you, in the last 2 or 3 minutes of the talk. But in joint work with Ankur Moitra and Colin Sandon, we actually studied the depth requirement of belief propagation, and these are words from theoretical computer science, AC0, TC0, and C1. These are deeper and deeper circuits. But what I should mention is that these 2 results are sort of true in general. And these 2 results is exactly in the situation that we talked about before. So this is below the Kasten-Stigom bound, KS bound. And in fact, just in very, very particular cases where Q is greater or equal than 5. Okay, so somehow the strongest depth results that we have are results that only hold in this regime of the Kasten-Stigom bound, where linear estimators don't work, and so on and so forth. Okay, so let me, there's a lot more I can say. Let me just mention, let me not mention in closing that we also know that belief propagation actually requires real numbers or requires infinite accuracy. So this answer a conjecture of that was in the original EKPS paper, and it's in this paper by Jane Kohler, Liu, and myself from a couple of years ago. And I'll stop here. What is the conclusion? The conclusion is that I started by BP is simple, belief propagation is simple, it's run in linear time. And what we showed is that, if d theta square is bigger than 1, let me write this more. If d theta square is bigger than 1, it behaves like a linear algorithm. It's really, there's many ways in which you can replace it just by taking the majority or by counting, or you can linearize it and get a linear algebra algorithm to solve your community detection and so on and so forth. So that's part of the picture that we get. But on the other hand, we learned that belief propagation is complex. So in this, when Q is bigger than 5, below the KS bound, the signal is fractal, there are statistical computational gaps, and it requires depth and precision. And I'll stop here, and I'm happy to take questions. Let me just thank the grant and thank you for your attention.
Okay, well, thank you very much for a wonderful talk. If you would like to ask a question, probably the chat would be best, but I could also allow you to talk, assuming that the system works, meaning that I can see your raised hand. So let me start with my first question. Obviously, these models are inspired by applications. So I would say, my question is this: applied, in applications, graphs are not so perfect as in theory and so on. What kind of assumptions on the mathematical side are most troublesome, in the sense that they are unrealistic, and in reality, that the models would behave differently than in your theoretical models?
Yeah, that's a perfect question, and I have the same. I don't know, you expressed it very politely, but I think in the phylogenetic literature, which is the first part, I think the models are not bad. The main issue there is what's called alignment. So the DNA sequences have to be aligned for this model to work, but there are parts of DNA sequences that are aligned because there are, something around them that is preserved. There's neutral mutations. Biologists know how to, at least in some cases, get information that looks a little bit like what we care about. I think in the block model application, the model is really bad. And I think the main reason that it's really bad is that it's rarely the case that you don't have any information about the nodes. Usually when I give you a network, a lot of, you don't just know the network, I know what languages people speak, I know what, at least for some of them, I know their political affiliation and so on and so forth. And there's definitely a lot of work in more bridging the theory and apply that try to see what, what extra do you get, from this fact. What was interesting for me working with the physicists is that even when you take these networks that I showed the picture of, sorry, let me try to show the picture again, is even when you show these pictures where, you actually have a lot of information about the network, right? So you don't actually need the algorithm because these are labeled networks, you know everything about them. You still see that, when you apply this linear algebra algorithm based on BP, actually the number of communities is often the number of real eigenvalues outside the square of d theta square equal to 1, right? So there's really, it seems like some of the picture is very, very robust. The model, especially in the block model, are terrible for almost all of the application of real networks, right? So that's, that's just real life. It's an excellent question. And, I often feel like, what do these models have with real life? And, it's not just the simplicity, it's also the fact that it's almost never the case that in networks, you don't know anything about the nodes. And again, I think the phylogenetic picture, it's really, the models really grew in biology, and there are more sophisticated models and so on and so forth, but I think that people understand at least some situation where these models make sense.
Okay, so I do not see any questions in chat, and I do not see anybody raising a hand. So in that case, let me ask you the second question, which is just curiosity, because when you were discussing the block model, you said about some initial conjectures coming from physicists. You referred to these people as physicists, if I remember correctly. So what kind of physics model they were interested in or inspired? I mean, what kind of physics?
So I didn't give the context to, because you have to make some choices, but this broadcast model on the tree, I just want to show the name. This broadcast model on the tree is very closely related to, maybe I'll write some name here. This is very closely related to what's called diluted spin glasses. And in fact, there's a famous paper of, there's a paper I like, I don't know if it's as as I should have had it, of Mezzard and Montanari, when I think this is when they heard about the reconstruction problem, and they said, okay, this is how we call many of these things in spin glass theory. So this is a paper around 06 or 07, when some of us who do the mathematics of these things talk to them, and they said, oh, we call the Kasten-Stigma bound this and this and this and this and this. So a lot of what they do in diluted spin glass is related to the reconstruction problem. Often it's not rigorous probabilistically, right? So they will linearize the system and will check the stability of fixed point and so on and so forth. But for them, the Kasten-Stigma bound is exactly where some linearization becomes stable or it's unstable and so on and so forth, right? So the Parisi school, right, they have done related calculation in their study of spin glasses for quite a while.
Okay, so it looks like I don't see any questions in chat. And once again, thank you very much for a wonderful talk. Oh, wait a minute. There is a question in part 2 you had. Do you see the question in chat, Elchanan?
Yeah, in part 2 you had a result that Limin greater than 0. Yes, Eugene, let me try to get to your question. Yes, I talked about it again. Let me go to this result that I had here. I think I know which result you're talking about. You're talking about this result, right? So what is this result? Okay, so this result is a way of thinking. So first of all, sorry for using different notation, slightly different notation. Here, I guess it should be x of h. Okay, so x of naught is the value of the root. We're looking at the conditional expectation of x of naught given x of h. The conditional expectation is like the conditional probability, right? Our value are plus or minus 1. So it just measures how close are you to plus or minus 1 given all of the information that you have on the leaves. If you have no information, then what you will have is that the conditional expectation of x naught given xh will go to 0 as h goes to infinity. Okay, you have to think it's a random variable, but will go, in some sense it will go to 0, right? So, it's a random variable that, will stay close to 0 or less than epsilon for every epsilon is probably going to 1 as h goes to infinity, right? If it doesn't, then it means that this random variable is non-degenerate. And non-degenerate, we just mean that it has a variance, right? And that's equivalent to the fact that the leaves have some information on the root. That's a good question. So I did this quickly, so that's a good question. Thank you, Eugene.
Okay. Okay, so there's another question. How do we know that the data?
So if we are only given the data without information on data, how do we know from the data if d theta square is bigger than 1 or not? So that is a good question. I think, thank you, Nan, that's a good question. So I think a little bit it depends on the setup. In the phylogenetic setup, if theta so let me give you some answer. In the phylogenetic setup, if the theta is the same for all the edges, which is actually not the assumption usually in phylogenetic, you can find just correlated nodes, find the nodes with the maximal correlation, you compute the correlation between them, you will get an estimated theta. You'll find another pair, you'll get another estimate for theta. You can average all of these estimates, you will get the theta. In the block model situation, actually, if d theta square is less than 1, you cannot find dn theta. Because in fact, some of our results, so that was in phylogeny, in block model, some of the results we proved it with Alan and Sly, is that if d theta square is less than 1, then the block model that we're looking at is contiguous to Erdős-Renyi random graph. In particular, you cannot find the theta, right? Because the theta, it's true if d theta, if theta is 0, it's true if theta is like 1 over d, it's true for various values of theta, you're going to find something that contiguous to, and it's not completely trivial to find the theta. In the same paper, if d theta square is bigger than 1, sorry, this is just for q equal 2. I mean, I was trying to make this is just for q equal 2. And in the same paper, in the case where q is equal to 2, we show if d theta square is bigger than 1, by looking at the statistics of the cycle, you can find dn theta, give you theta. Okay, so I won't say exactly how you do it, but the larger theta is the more short cycles you have. So that's an excellent question too. Thank you, Nat.
Okay, well, let's see. If there are no more questions, then I guess, once again, thank you for an excellent talk. And once again, congratulations on the
Thank you very much,
medallion.
Chris. Thank you, everyone, for attending and for the questions.
And that's right. Thank you. Thank you, everyone for coming to the talk.
Thanks for sharing, Chris. It was good. Thanks.
Okay.
Good to see you.
Bye.
Bye.